Good afternoon. Today the topic of my lecture will be on the design, that is the optimal design and development of a 3-finger exoskeleton. The organization of today's lecture will be as follows. First we have the introduction, in that we will be seeing quickly the objective and the motivation of this work, and then the methods involved in designing the optimal hand exoskeleton. The first method is finger motion capturing of the human flexion motion, and then the development of 4-bar synthesis mechanism based on 3 position analysis motion synthesis of a 4-bar mechanism. Then we have the optimal 4-bar mechanism synthesize, then we see the redundancy resolution, and finally resolving redundancy resolution in object translation task. Coming to the introduction, the objective is to understand the human finger physiology, how the joints are connected, how the links are connected by the joints, by the physiological joints, so that we design an optimal exoskeleton for the 3 fingers, that is for index, middle and thumb digits. Coming to the motivation followed by the accomplishments, optimal design of a 3-finger exoskeleton to track the human finger motion accurately, so that it can be used for both assistive and rehabilitative purposes. And human finger joint cannot be modeled by a single revolute joint because of the changing instantaneous center of rotation of the human joints, and hence 4-bar mechanism based finger exoskeleton is designed optimally in this work. The kinematic model of the designed exoskeleton is proposed, is made or is modeled, and the exoskeleton is fabricated in the rapid prototype form, and then finally redundancy resolution of the designed exoskeleton is performed. But in this lecture we will be seeing up to these 4 points, that is we will be seeing the optimal design, and we will be seeing how the 4-bar mechanism can be generated based on 3 position analysis, and then the kinematic model, and finally the fabrication of the exoskeleton. The redundancy resolution will be seen in the next lecture. Coming to the methods, we see that human joints is modeled in such a way that we have in general the PIP joint of the 4 digits is with the hinge, that is the revolute joint, and the MCP joint of the digits 5 digits are of ellipsoidal form, which is shown here, and the thumbs joint is, that is the CMC joint, carpometacarpal phalangeal joint, is made up of this shape, which is the saddle shape, and hence we have designed our exoskeleton for these 3 digits based on such degrees of freedom, which is finger exoskeleton having 3 degrees of freedom, and the middle exoskeleton, middle finger exoskeleton also having 3 degrees of freedom, mainly for the flexion extension and also the middle finger doing flexion extension. But the thumb we have designed with 4 degrees of freedom, where 3 degrees of freedom for the thumb exoskeleton's flexion extension and 1 degrees of freedom for the abduction adduction. Hence totally we have designed an exoskeleton for these 3 digits with 10 degrees of freedom. Now comparing the human phalanx trajectory with that of the link made up of revolute joint and with that of the 4-bar mechanisms. So you can see that the red trajectory is the one traced by the human phalanx having the instantaneously varying joint centers, and that trajectory is also traced by a link with a revolute joint, that is the link with a single point joint, due to which what happens here is the error is increasing because the traversing path deviates more and more as it goes till the end point, whereas the same trajectory, that is the desired human trajectory, is traced by a 4-bar mechanism. In that case, due to the instantaneously varying center of the 4-bar mechanism, we could able to trace the human desired trajectory. That is what is shown here in this figure. And now coming to the methods, which is of tracking how the human, yes. So as you can see that here the markers are placed on the human finger in such a way that on the lateral surfaces of these 3 phalanges, 3 markers in the form of a triangle are placed on the finger phalanges, so that the subject is asked to move a flexion extension motion and then the camera which is placed on the top of this plane captures the motion, that is a planar motion which is in the plane of flexion extension of the finger, and those trajectories of those 3 markers, red, blue and green markers, are traced in such a way that they are used to generate the 4 bar mechanism. So, the desired 4 bar mechanisms for each phalanx is given by this notion, that is for the index finger we have 3 4 bar mechanisms, that is for the proximal phalanx and the middle phalanx, then for the distal phalanx. So, these 3 4 bars are serially attached so that they can be meant to move the index finger in the flexion extension motion without taking the finger phalanges in a diversed way. So, that precisely we can see that for the, this is the figure for showing the 4 bar mechanism for the proximal phalanx alone, and this is the figure which shows the 4 bar mechanism for the middle phalanx alone, and this is the 4 bar mechanism for the distal phalanx alone, and these 3 phalanges are serially connected to form the index finger exoskeleton. This is the concept, and this is the quite good idea we have to develop or to design from the previous video which I have shown here with this video. So, now similar way for the middle finger also we place the markers in the lateral surface as shown here and obtain these 3 4 bar mechanisms attached serially, and likewise for the thumb we have 4 bar mechanisms, one meant for the abduction adduction motion or degrees of freedom and 3 more for the flexion extension of the thumb. Now, coming to the major part of the methods, which is the 3-point analytical motion synthesis of a 4 bar mechanism. So, as can be seen here, due to that motion, that is the flexion extension motion of the index finger, we have 3 desired trajectories, one by the proximal phalanx and the other one by the middle phalanx and then the third one by the distal phalanx of the index finger. So, having these trajectories, we are going to generate the 4 bar mechanism based on 3 position analytical motion synthesis method. So, in that we take 3 different points P1 from the start of the trajectory. For example, we consider first the proximal phalanx alone. So, we take this 4 bar this marker's trajectory such that it is meant for the proximal phalanx alone. So, for the proximal phalanx from this trajectory we take the start point and the middle point and then the end point. These 3 points are taken for the 3 position analytical motion synthesis of a 4 bar mechanism, that is P1, P2 and P3. So, now we take this diagram schematic as shown here, where G1, where L1, L2 and this is the coupler L3 and then L4 or the link lengths of the 4 bar mechanism, where L1 is the ground link and L2 is the crank link, L4 is the rocker link and L3 is the coupler. And now we take these positions, that is P1, P2 and P3. These are the start, intermediate and the end points from the trajectory traced by the proximal phalanx red marker. Then, as shown in the schematic, we see that V1, vector V1, this is vector V1 that is pointing from point A1 to B1, that is vector V1 is given by D1 minus S1 as can be seen here, that is equation 1. Similarly, vector G1 is C1 plus V1 minus R1, that is the second equation as can be seen from this schematic. Likewise, we have C2, that is C2 plus D2 minus P21. P21 is the vector connecting between the points P1 to P2, minus P21 minus D1 minus C1 is equal to 0. Likewise, C3 minus plus D3 minus P31 and minus D1 minus C1 equal to 0. So, the 4 equations how we have obtained I have described here from the schematic. Then from this, having the complex notations, we can have the vectors represented by this notations, which is given by the complex notations given by C e power I theta plus alpha 2 plus D e power I into omega plus beta 2 minus P 21 e power I delta 2 minus S e power I omega minus C e power I theta equal to 0. Similarly, the equation 6 also obtained based on the complex notations of these two equations 3 and 4, where C D are the vector magnitudes or the magnitudes of the vector C and D respectively. And now coming to this equation 7 and 8, by simplifying these equations, that is by taking these two P21 and P31 part in the right hand side, we have the equations 7 and 8 obtained from equations 5 and 6. So, in continuation, then we have 4 equations 9 to 12 from the by having this representation of that is e power polar form e power plus or minus I theta equal to cos theta plus or minus I sin theta. So, with that representation we could have these 4 equations 9 to 12 coming up from this 2 equations previously 7 and 8. Then for these 4 equations, that is 9 to 12, we have 12 variables, that is C, theta, alpha 2, alpha 3, D, omega, beta 2, beta 3, delta 2, delta 3 and vectors P21 and P31. Basically it must be small P21 and small P31. Okay. So, these are the 12 variables with those 4 equations, and these are solved for the magnitudes theta, that is magnitude C and D, and angles theta and omega. So, these equations 4 equations can be solved for these 4 variables, that is C, D, theta and omega for the vector C and D, provided we give other 8 parameters a priori. And now in continuation, so we represent from the 4 equations, if we represent or if we assume ML equal to sin alpha minus 1 and NL equal to sin alpha 2 and O2 equal to cos beta 2 minus 1, QL equal to sin alpha 2, FL equal to P21 cos delta 2, similarly HL equal to cos alpha 3 minus 1, IL equal to sin alpha 3, JL equal to cos beta 3 minus 1 and KL equal to cos beta 3, LL equal to P31 cos delta 3, then VL equal to P21 sin delta 2, then omega, that is WL equal to P31 sin delta 3, C1x is equal to C into cos theta, then C1y equal to C into sin theta, then D1x, D1y are given by D cos omega and D cos D sin omega respectively. Then we will have a standard matrix form which is given by this equation, that is matrix multiplied by a vector equal to this vector. This standard matrix form will be obtained provided we assume this ML equal to this for the previous 9 to 12 4 equations. Then we will have the magnitude, by solving this matrix form we will have the magnitude C and D and the angles theta and omega of the left diet. This is the left diet, that is this vector pair is the left diet. This vector pair is a diet, a vector pair is a diet, and the forebar has left diet and the right diet. Now we have solved the magnitude for the left diet, that is C and D for this vector C1 and D1. Similarly, theta and omega for that is theta between the ground link and the crank link, and omega, that is the between the x axis and the vector D1 of the left diet of the forebar mechanism, are obtained by solving the standard matrix form, which is obtained by assuming these values for the previous equations 9 to 12. Then similarly we can also do the same procedure in order to get the standard matrix form for the right diet, that is obtained by the vector pair R1 and S1. So we can also obtain the standard form of the matrix which is given by this equation, that is matrix having the members MR, NR, OR, QR, HR, IR, JR, KR, NR, MR, QR, OR, JR, HR, KR and IR. So, we have by solving these equations, this standard matrix equation, we could solve for the magnitude R and S and the angles delta, that is sigma and phi for this right diode, which is given by this expressions R equal to root of R1 x square plus R1 y square, and similarly S equal to root of S1 x square plus S1 y square, and sigma and phi are given by this expressions which is tan inverse of R1 y by R1 x, and phi equal to tan inverse of S1 y by S1 x. Now, having solved this, we should also see how we could give the variables, that is the alpha 3 and alpha 2, how that can be obtained, because that is a value which we could able to obtain by the marker positions. That is why we have taken the marker in the form of a triangle with 3 marker points, red, green and blue. So, thus having solved that right diode magnitude and the angles and the left diode magnitude and the angles for the given fixed pivot points, that is O2 and O4, and the 8 parameters, that is alpha 2, alpha 3, beta 2, beta 3, P21 vector, P31 vector and the angles delta 2 and delta 3, a 4-bar linkage mechanism can be determined using the 3 position motion synthesis methodology. Now, coming to the computation of the angles alpha 2 and alpha 3. As can be seen here, we could get that alpha 3 and alpha 2 are given by 2 tan inverse of the expression which is given in terms of K2, K1 and K3. Likewise, A2, A1, A3 and A6 in terms of beta 2 and beta 3, where these variables or the parameters or the expressions for K1 till K3 and A1 till A6 and C1 till C6 are given here, which I can read it very fast. So, K1 is equal to A1, A2, A4 plus A3, A6, K2 equal to A3, A4 plus A5, A6. Similarly, K3 equal to A1 square minus A2 square minus A3 square minus A4 square minus A6 square by 2, where A1 is equal to minus C3 square minus C4 square and A2 equal to C3 C6 minus C4 C5 and A5 equal to minus C4 C6 minus C3 C5. Similarly, we go up to A6, then we have C1 in terms of beta 2 and eta 3 minus similarly it goes up to C6. Thus, having these 8 parameters, that is alpha 2, alpha 3, beta 2, beta 3, delta 2, delta 3 and P21 and P31, which is the vectors connecting from the point P1 to P2 and P3 to P1, we could able to have the 4-bar mechanism provided the pivot points are obtained from this user. And now, going to the optimal 4-bar mechanism. So, where comes the optimization? So, now we are going to the optimization after the 3 position synthesis of the 4-bar mechanism. Now, we see that where is optimization coming into picture. So, having placed the marker on the finger phalanx, so we want the 4-bar mechanism in a way that is the optimal 4-bar mechanism, so that the discrepancy between the desired human trajectory, that is the darker line here, and the dotted line, that is the trajectory traced by the 4-bar mechanism, must be minimized. That is, the discrepancy between the desired human trajectory and the actual 4-bar coupler trajectory must be minimized. That is the error here, which is given by the symbol phi. And you can see that the 4-bar mechanism is the one which has the ground link, say L1, and the input link, which is the actuating link, that is the crank link L2, then this is the coupler which is L3, and then we have the rocker which just follows the based on the input it rocks, that is the L4, that is the output link you can say, and the input angle is theta and the output angle is sigma here, and the dotted line is the desired trajectory, and the thick line is the desired trajectory and the dotted line is the trajectory of the coupler point. Now coming to the general optimization strategy. So here we have 10 design variables such that P1x, P1y, similarly O2x, O2y, that is the pivot points, one pivot point in the left and one pivot point in the right. So we have 4 here, 2 plus 2 4 plus this point P1x, P2, P1y, then we have the link lengths L2, L4, O, that is theta and sigma. So these 10 design variables can be obtained from the general optimization strategy, but the alternative smart optimization trajectory strategy is that we could have the 4 design variables to be obtained from the optimization methodology in such a way that by giving the input or the parameters a priori, the other 6 parameters, thus it can be having only the O2 and O4 points, that the pivot points will be the design variables of the optimization output. Now coming to the objective function, we have framed the objective function such that the discrepancy between the human path and the coupler path, thus phi equal to summation I equal to 1 to n di square, where di is the discrepancy of the human point at that instant and the coupler point at that instant I. And the procedures steps to get the optimal 4 bar are: perform the 3 position generated motion generation by analytical synthesis using fixed pivot points, that is the design variables suggested by the optimization algorithm. We have used the genetic algorithm optimization technique from the MATLAB toolbox. Then evaluate the objective function, then check whether the constraint is not violated, and then replace the previous design by a new one. That is how it continues and goes for the convergence. And now coming to the kinematic model of the index finger exoskeleton, having designed the 3 finger exoskeleton, first we see the kinematic model of the index finger exoskeleton. So we have designed in such a way that the first 4 bar is for the proximal phalanx, and the second 4 bar is for the middle phalanx, and the third 4 bar is for the distal phalanx, and these 3 are connected or attached serially as shown here in this figure on the left. Likewise, we go for the index fingers kinematic model, which is a forward kinematic equation where the xf, that is the planar tip xf and xy, is given by these expressions in terms of the link lengths and the angle parameters, which is having delta, sigma and alpha. Based on them, that is for the proximal phalanx delta, sigma and alpha, and for the middle phalanx delta, sigma and alpha, and for the distal phalanx delta, sigma and alpha. For all these collectively the tip can be obtained, that is xf and yf. That is starting from this point we could able to reach here and then go here, then from there you reach here, then from there you can go here, then reach here, then reach here, then reach the tip. That is from the closed loop equation method we could able to reach from the start point O2 till the tip position by this forward kinematic equation. Thus given the input theta, theta d, theta m and theta p, that is theta p is the input angle for the proximal phalanx and theta m is the input angle for the middle phalanx and theta d is the input angle for the distal phalanx, distal 4 bar. Having these 4 bar input angles, we could able to get the tip position, that is xif and yif equation. So apart from the theta p, theta d and theta m, other parameters are the constant values. Now similarly for the middle finger, the optimal middle finger exoskeleton is obtained by these 3 4 bar mechanisms. Similarly as in the case of index finger, we have the 4 bar mechanism optimal one designed first for the proximal phalanx, then for the middle phalanx and then for the distal phalanx, and they are connected serially such that the optimally designed serial 4 bar mechanism based index finger is shown here. For the middle finger is exoskeleton is shown here in the left side. And then likewise for the index finger exoskeleton, the tip forward kinematic equation for the middle finger exoskeleton tip is given here, which is also the function of sigma, delta, phi, alpha of the 3 4 bar mechanisms, that is proximal, middle and distal of the middle finger. Finally, we come for the kinematic model of the thumb exoskeleton. As can be shown here, the first 4 bar mechanism is considered for the abduction adduction motion, that is given by the subscript A by A, that is abduction adduction, and then we develop the second 4 bar mechanism for the flexion extension of the same phalanx, then the middle phalanx 4 bar mechanism for the middle phalanx, and then for the distal phalanx. We have computed and we have designed it, and hence the attachment is like this, that is this 4 bar mechanism is in one plane and the serially connected 3 4 bar mechanism meant for flexion extension motion is in the plane which is perpendicular to this abduction adduction 4 bar mechanism plane. And then due to which the 4 bar thumb exoskeleton having 4 bar mechanisms meant for both abduction and flexion extension movements, it has the tip motion coming in the 3D position. Thus, it is given by xth, x yth and zth, given by this expression, which is also based on the angles, that is delta, sigma and phi of these 4 mechanisms, that is 4 bar mechanisms, and the inputs for, that is the joint variables, that is the generalized coordinate for this thumb exoskeleton is theta p abduction adduction and theta m theta t. These 4 joint variables are the generalized coordinates for this thumb exoskeleton. And now coming to the optimal parameters, that is the final optimal parameters of this index finger, middle finger and the thumb exoskeletons. So, as can be shown in the table here, we have the optimal link length parameters of each 4 bar mechanisms, that is proximal, middle and the distal mechanisms, and everything lengths are given in the centimeters. And now we can see that, as you can see that simulation of the 4 bar serially connected 4 bar mechanisms for the index finger exoskeleton in tracing the desired trajectory, and you can see here this is the trajectory of the instantaneous joint center of the 4 bar mechanism, and you can see that here you can have the trajectory compared with that of the link having the revolute joint and with the 4 bar mechanism with that of the human trajectory. Similarly, we can see for that of the 4 bar mechanism of the middle phalanx and for the distal phalanx. Likewise, for the middle finger exoskeleton, we have the trajectories varying here, and instantaneous trajectory of the 4 bar mechanisms also shown here. Then we have this video coming out for the middle finger exoskeleton, and these are the optimal parameters of the middle finger exoskeleton. Then we have finally the thumb exoskeleton, that is for the flexion extension and also for the abduction adduction motion, and thus it has 4 degrees of freedom, and all these parameters are given here, that is the link length parameters for all the 4 bar mechanisms, totally 4 number of 4 bar mechanisms. We have the trajectory comparison for each 4 bar mechanisms with that of the serial link, and then we could also take the work volume of the 4 bar mechanisms for each exoskeleton, that is the index finger exoskeleton, middle finger exoskeleton and the thumb exoskeleton. So, 3D view both in the side view and the top view. Then finally, we have the rapid prototype of the developed or the optimally designed 3 finger exoskeleton. As you can see that this is made up of acrylic material. The prototype is made up of acrylic material, and we have the clamp also having the motor attached to this each 4 bar mechanism to have the motor attached to it, and this is the complete prototype of this 3 finger exoskeleton designed optimally for this 3 fingers, that is the index finger, thumb and the middle finger. Then you can see here how the motor is attached. Let me closely show that. Here the motor shaft is attached to the 4 bars input link, because the input link is acting as a crank link which is going to give the angle to the mechanism, and the other two links will, that is the coupler link and the rocker link, will behave in such a way that the coupler can trace the desired human trajectory. So, as you can see that the motor shaft is attached to the link of the crank, and then this is the rocker link, and we have the coupler here. Then this 4 bar mechanism, that is, this is the distal 4 bar mechanism, it is placed on the just above the coupler, that is, this is the coupler of the previous 4 bar mechanism. That is, if this is the distal 4 bar mechanism, then this 4 bar mechanism is placed on the coupler of the middle 4 bar mechanisms. And as you can see that the clamp is clearly shown here. It is the clamp, it is a metal element which is clamping the motor in such a way that it is attaching the top and bottom surface of the full 4 bar mechanism, so that the planes, that is, this is the plane having the link and this is the plane having the coupler. Yeah, with this we could wind up this lecture, which is the optimal design and development of the 3 4 bar based index finger, middle finger and thumb exoskeleton. Thank you.